You would have seen the second problem. Yeah, this problem. E power integral tan x dx would be sec x, right? You realize that e power integral tan x dx would be e power ln sec x. So sec x. So the solution to this differential equation evidently is y e power, so y sec x integral x squared cos squared x sec x dx, and this becomes cos x, and you can integrate this using parts, right? You can integrate this by parts, integration by parts, differentiate this and integrate this. You can do the needful. All right, that's the solution to this differential equation. Also, sorry?
Sir, integration of tan x is log mod sec x.
Yeah, we are assuming that. We are assuming that. I mean, it's sec x is greater than 0. We'll assume that. Whenever in these solutions, we'll assume that. Not a problem. Problem 4, for example, is a slight variation. X plus 2y cubed dy dx is y. Now this dy dx is y by this is not a linear in y. In fact, you may want to write this as dx dy equal to x by y plus 2y squared, right? Or dx dy minus 1 by y into x is 2y squared. This is a linear in x. It's a linear in x. P is minus 1 by y, q is 2y squared. The solution to this differential equation would be x e power integral p dy is integral q e power integral p dy dy, right? So the solution to this differential equation is x e power integral minus 1 by y dy would be ln 1 by y. So this would be x by y, right? That's equal to integral 1 by y 2y squared dy, etc. Got me? So that's a regular linear differential equation. Now some differential equations may not necessarily appear in the form, let's say dy dx plus py equal to q, or dx dy plus a linear in x, etc. Sometimes you may have to go one step away to convert it into a linear form or make it look into that linear form. Something, it may be a little camouflaged. All right. For example, a differential equation of the following kind: dy dx plus py is qy to power n, where p and q are functions of x. A differential equation of this kind, dy dx plus py, is q into y to power n, where p and q are functions of x. P is a function of x, q is a function of x. Now, for such a situation, what you do is you multiply both sides by y to power minus n. Equal to q, right? Hey, y to power minus n dy, realize, is d of something. D of what? Integral of y to power minus n. Integral of y to power minus n is y to power 1 minus n by 1 minus n. Yes or no? Which is like 1 by 1 minus n d of y to power 1 minus n, right? So this y to power minus n dy could be written as 1 by 1 minus n d of y to power 1 minus n dx. That's how you could write this term as y to power minus n dy. I could write as 1 by 1 minus n d of y to power 1 minus n, yes or no? Plus py to power 1 minus n is q. You may then want to make y to power 1 minus n the subject of integration. It could be a linear in y to power 1 minus n. it now becomes a revised linear in y to power 1 minus n, because you may want to write y to power 1 minus n as some z, in which case the equation becomes dz dx plus 1 minus n into p z equals 1 minus n into q. Do you realize that now it's a linear in z? It's a linear in z, and the new p is p into 1 minus n, and the new q is q into 1 minus n. So the solution to this differential equation would be z e power integral 1 minus p dx is integral q into 1 minus n e power 1 minus n p dx. Instead of p you have 1 minus n, instead of y you have z, instead of q you have q into 1 minus n. So it gets reduced to a regular linear equation. Alright. In fact, this form of the differential equation is often referred to as the Bernoulli's form. This form of the differential equation is often referred to as the Bernoulli's form. Essentially, it's a ramification of the regular linear differential equation only, right? Eventually it gets reduced to a regular linear differential equation. Is that all right? Do you all understand the solution to this differential equation? Now let's quickly have this illustrated. Section E. We have, let's say, problem 1, for example, y ln x minus 1 y dx is x dy, or we have like a dy dx. See, dy dx, x dy dx is y squared ln x minus y, or you may want to divide by x both sides, or you get like a dy dx plus 1 by x into y equals y squared ln x by x. What is it that you may want to do now? You may want to divide by y squared, y to power n, right? Divide by y to power n. So divide by y square both sides, right? It's now Bernoulli's form. Dy dx plus p into y is q into y to power n. So multiply by y to power minus 2 both sides essentially, right? So if I multiply by y to power minus 2 both sides, then I get 1 by y equals this. And 1 by y squared dy dx, realize, is minus 1 by minus ddx of 1 by y. Yes or no? Y to power minus 2 plus 1 divided by minus 2 plus 1, right? Y to power minus 2 dy is d of y to power minus 1 divided by minus 1. So you get minus ddx of 1 by y. So this I can write as minus ddx of 1 by y plus 1 by x into 1 by y equals ln x by x. So do you realize it becomes a revised linear? It becomes a revised linear in 1 by y. It becomes a revised linear in 1 by y. Clear? So you can say dt dx plus p into t is q, and so on and so forth. You can proceed, and then you can solve the linear differential equation as per the result provided to you. Sounds all right? Let me just illustrate one more on this. Problem 2. Sec squared y dy dx plus x tan y is x cubed. See, the sec squared y dy dx can be written as d dx of tan y plus x tan y is x cube. So do you realize it's become a linear in tan y? See, it's now like a dz dx plus x into z is x cube, linear in z, where p is x and q is x cube. The solution would be z e power integral p dx is integral q e power integral p dx dx. Right? So it could be converted into a linear, even if it's not presented in a linear form, it could be converted into a linear form like we did here. Got me? So a large number of problems of this type, this variety, would be common for the sake of examinations, would appear in examinations, and in fact I'll tell you where you've encountered this. We were solving this problem on EMI. There was a capacitor, there was a BLAT and stuff, where you encountered a linear, but we solved it a little differently then because I had not taught you how to solve linear differential equations. Now if you get an opportunity to revisit that problem, you can connect the two things. It will fall in place. All right. Now, another form of the differential equation dy dx ax plus by plus c divided by a prime x plus b prime y plus c prime, where these two lines are not parallel. These two lines, this equal to 0 and this equal to 0, are non-parallel lines. That means where a by a prime is not equal to b by b prime. That means a by b is not equal to a prime by b prime. Then this equal to 0 and this equal to 0 would be non-parallel lines. If this equal to 0 and this equal to 0 are non-parallel lines, they do intersect at a point. They do intersect at a point. Now to solve this differential equation, we bring about a certain transformation. The transformation that we suggest to solve this differential equation, in the event these two are non-parallel lines, is, let me say, small x that appears here is some capital X plus h, small y is some capital Y plus k. This is like translation of the coordinate axis. We move from the small xy axis to the capital XY. We move from small xy to the capital XY, where I define this hk as the intersection of these two lines. I define the hk as the intersection point of these two lines. This equal to 0 is a straight line, this equal to 0 would be a straight line, and hk, I say, is the point where the two lines intersect each other, is the point where the two lines intersect each other. That means ax plus by plus c equal to 0 would be a line, a prime x plus b prime y plus c prime equal to 0 would be another line, and I say that hk is the point of intersection. Hk is the point of intersection of the two lines. That means hk can be obtained by solving these two simultaneous equations, ah plus bk plus c equal to 0 and a prime h plus b prime k plus c prime equal to 0. I can solve for h and k. I can solve for h and k. This is how I select my HK for this translation, from small xy to capital XY. Now, very clearly then, H and K are fixed numbers. Dx is then d of capital X and dy is d of capital Y. Do you realize that? So this d of small y divided by d of small x could actually be written as d of capital Y divided by d of capital X. I could write this left hand side this way. So now I'm actually moving from small xy to capital XY. So I replace the x and y here by capital X plus h and capital Y plus k. So I get like a into capital X plus h plus b into capital Y plus k plus c divided by a prime x plus a prime capital X plus h plus b prime capital Y plus k plus c prime. Hey, but ah plus bk plus c is 0, and similarly a prime h plus b prime k plus c prime is 0. So then this reduces to a times capital X plus b times capital Y divided by a prime x plus b prime y. Now realize that this is a plus b y by x divided by a prime plus b prime y by x. Hello? When I divide by capital X, this is what happens. Hey, what form is it? Homogeneous form. So I can take y by x as v and I can solve the differential equation. I can take capital Y by capital X as some v and solve the differential equation. So what is it that I arrive at? A relationship between capital Y and capital X, and then eventually I can replace the capital Y by small y minus k and capital X by small x minus h in the final solution. So I would get a relationship between small x and small y. That would be the solution to that differential equation. Got me? So that's provided these two lines intersect. Only then you can find a finite value of h and k. But if these two lines were parallel to each other, then hk won't be available to you, right? If these two lines are parallel to each other, then you can't find an hk. Then what is it that we should do? Let's examine what we got to be doing. In the event the two lines are non-parallel. In the event they are parallel, this is what we do. If they are, in the event they are non-parallel, this is what we do. What if they are parallel? If they are parallel, I can't find hk, the point of intersection of the two lines. Once that happens, if the two lines are parallel, then we deploy the following. Can I wipe this off? Suppose ax plus by plus c equal to 0 and a prime x plus b prime y plus c prime equal to 0 are parallel lines. Suppose they are parallel lines. If they are parallel, it would mean a by b must be equal to some a prime by b prime, each would be some lambda. If they are parallel, then this must happen. A by b must be equal to a prime by b prime, each equal to lambda. Which means I can write this a as lambda b and this a prime as lambda b prime. So once I do this, I write a as lambda b and I took b common from this, then this is going to be a b into lambda x plus y plus c divided by this a prime replaced by lambda b prime. So b prime into lambda x plus y plus c prime. Hey, does it ring a bell? This is f of ax plus by, isn't it? This is right inside is a function of f of ax plus by. A is lambda and b is 1. So what substitution is warranted here? Yeah, lambda x plus y equal to some z. This will work. The variables will then get separated. You can solve for z in terms of x like I discussed earlier. Right? This is what you got to be doing. Got me? So you know what to do when they are not parallel. You know what to do if they are parallel. Obviously, this would take fewer steps to solve than the earlier one. Okay. Can I wipe this off? Another differential equation which would be of interest to us is what's called an exact differential equation. An exact differential equation. For example, I have x cube cos y dy plus sin y 3x squared dx equal to 0. Suppose something like this. X cube cos y dy is sin y 3x squared dx. See, I could write this as x cubed into d of sin y, right? Cos y dy is d of sin y plus sin y d of x cube equal to 0. Hey, if you recall, x dy plus y dx, algebra of differentials, we got as d of xy. See, it's x into dy plus y dx kind of a thing. So that's going to be d of xy. So this is going to be d of x cubed sin y, that equal to 0. And if d of this is 0, that means this must be a constant. This would imply x cubed sin y equal to c. If d of something is 0, then that something must be a constant. Now this kind of a differential equation, which could eventually be reduced to d of something equal to 0, is called an exact differential equation. This is an example of an exact differential equation. We have like a something into dx plus something into dy, something into dx plus something into dy being reduced to d of something equal to 0. D of something equal to 0, that's an exact differential equation. So we have like a m which could be a function of x and y dx plus n in general a function of x and y dy, n a function of x and y dy equal to 0 would be an exact differential equation. Not all equations of this kind would be exact. This would be exact if it could be reduced to d of some u equal to 0. If it could be reduced to d of u equal to 0, then the above would be exact. Then the above would be an exact differential equation. Without getting into too many details related to the exact differential equations, without establishing those things, let me just state a few things related to the exact differential equation. First of all, how would one know if a differential equation is exact or not? One would have to carry out the following test. and this is without proof. To be exact, it would suffice. To be exact, it would suffice if when you differentiate m with respect to y, when you differentiate m with respect to y keeping x constant, that is dou m dou y, differentiating m with respect to y keeping x constant, that's dou m dou y. If that turns out to be dou n dou x, that means differentiating n with respect to x keeping y constant. If this condition is respectively met, then you know that you could convert this into an exact differential. You could convert this into an exact differential. If dou m dou y turns out to be dou n dou x, then the equation is said to be an exact differential equation. You could then write it as d of something equal to 0. For example, look into the sheet. There would be one section titled F containing exact differentials. Can I wipe this off? Ax plus by plus g dx plus hx plus by plus f dy equal to 0. First of all, whether I could, in order to solve this differential equation, see, one thing that you could always do is you could write dy dx as linear by linear, one of the known forms, but that's very cumbersome. It's time consuming and it causes a lot of pain. Too many stages involved, you're prone to making errors, right? Check if you could directly, with some little adjustment or manipulation, write it as d of something equal to 0. That means if this expression could be written as d of something, right? This is my m and this is the n, right? Now what's dou m dou y? Differentiate m with respect to y keeping x constant, you get b, right? You get b. What is dou n dou x? Dou n dou x h. Is it exact? It's not exact. There must be a mistake. B must be equal to h. This is a mistake here, obviously. I mean, if b were to be equal to h, then that would have been fine. I mean, if this was h, then it would make sense. See, then if this was h, then dou m dou y would be h and dou n dou x would be h. It would then be a exact differential. Then you can have you can muster some courage to reallocate and realign terms to get a perfect differential out of it, because now you can write this as ax dx, see, ax dx plus by dy plus h into y dx plus x dy plus g dx plus f dy